Well, this is why this is less than that is clear, I think. But the epsilon was, where's that stupid thing gone to? Epsilon equal to 1/2 f prime of a. So that's just this, and then they cancel and delta over 2 and delta 2. I'm just forgetting why it is that this. Yeah, it probably is. I need more RAM. You know what I mean? Huh. Well. Oh, that's the mean value theorem. See, if this divided by that is less than or is equal to phi prime of c, and phi prime of c is less than or equal to 1/2, so this to that is the mean value theorem. That's what I'm talking about here. This to that is mean value theorem. I should probably make a homework problem about this. Other books have this like set apart as like a lemma, but Edwards kind of just uses the mean value theorem in places without explaining it sometimes. But anyway, so we have that. Therefore, phi of x is in here, which means that we've shown that phi maps from this closed interval to this closed interval. And if we pick x and y in the closed interval, then what happens? Well, by the mean value theorem, there exists a c such that the difference of phi of x and phi of y is phi prime of c when, like, we look at this, right? And so the absolute value of this is equal to that, but that's less than or equal to 1/2. So indeed, the contraction constant's 1/2. And as such, we can apply Banach's fixed point theorem, and we get a unique x star in this closed interval for which phi of x star is equal to x star. But when you look at the definition of the contraction mapping here, that serves the purpose of getting f of x star equals to y star. So like to motivate it, we start by looking at the problem we're trying to solve, we linearize it, and then we look at a way to continue making that linearization approximation over and over again somehow. All right, and as such, we'll usually be able to formulate that as a contraction map. And because you can do that at each y, you can do that for each y in, V, you can define g of y to be the point x that it converges to and solves this. That means you can string those together and make g define a local inverse function for f with respect to the set u. And in fact, the inverse function in some sense will be the limit of the sequence of functions. You could look at the inverse function as the limit of a sequence of functions. And I actually calculate a few here because this was earlier in the weekend when I still thought I had time to do examples. This first example is amazingly easy. Like, this is a really neat thing that happened. So keep in mind, I'm just doing the iteration up here. So to find the inverse function, I take near a, the 0th one is a, and then the next one I take the last, to get the next one, I take the last one and I take f of the last one minus y divided by f prime of a. Okay? So I looked at f of x equals to the reciprocal function and I let a equal to 1. So in this case, f prime of 1 is minus 1. All right? And so my a and the b are both 1. G naught of y is 1. G1 of y is 1 minus this, which is 1 plus 1 minus, oh man, dudes. There's a typo here, but it does work out to minus y. And I am not going to let this, we are forging on. G2 of y then is minus y minus this, but that gives you 1 over y. And then the funny thing is, once you get to 1 over y, the iteration stops. So like when I plug in 1 over y minus 1 over 1 over y minus y, we take 1 over y minus 0. So this particular instance, the sequence of inverse function, sequence of approximates to the inverse function actually converges to the inverse function. after 3 steps. This gave me hope that perhaps I could find it happen again for some other example. But this hope is invalid. What happens for the same function, the reciprocal function, if I try to find an inverse at a half? When I try to find the inverse at a half, the derivative gives me -4. And this is the iteration. And when I do that twice, I get to this. And it just gets worse past here. It gets much worse. It gets worse. Notice that the sequence, it's taking function of function of function of function of function of function as you go on. So this is a sequence that every level of the function involves yet another composition of the previous step. It's quite horrible. Here's e to the x. I tried to see, well, maybe I can find the power series for log popping out or something. So here's what happened when I tried the iteration for e to the x. I got, all right, so nothing, just nothing. Now there's an example in Edwards. He tries to find the local inverse to x squared minus 1 with a equals to 1 and b equals to 0. So here f prime of x is 2x, which means f prime of 1 is 2. And so here's the iteration. What's it look like? This is what you do. And when you get to the first one, you get this. You get to the second one, you get that. And this is kind of nice. It's kind of nice, right? And then the third one gives you this. It's still nice. And then you're like, oh, wait, maybe something's happening here. So you can actually find the inverse function, right? Just solve for x. You get x plus or minus squared y. And quick Calc 2 refresher, this is, the binomial series, which you can derive from Taylor's theorem. And if you look at that, the fourth order term has a -5 over 128, whereas the fourth order term here has a -1 over 128. So it's almost the binomial series for the inverse function, but it ceases matching it at order 4. And anyway, Edwards is careful not to include the order 4 term. It's like, wait a minute, why do you leave off the order 4 term? Well, it's because it's not the binomial series after that point. Anyway, my point to you is just that it's ugly. Very, very ugly. That brings us to the multivariate mean value theorem. So, it would be lovely if the multivariable mean value theorem was as simple as the single variable mean value theorem. So like the mean value theorem for calculus of one variable says this, right? F of b minus f of a divided by b minus a is f prime of c for some c between a and b, right? But to generalize this, it's not as simple as it seems. Let me kind of try to explain to you why. To start with, though, I need to tell you what's the definition for the derivative of a mapping from Rn to Rm. So like, if you want to differentiate a function from Rn to Rm, what you need is a function here, a linear map from Rn to Rm such that you take f of p plus h minus f of p minus L of h, all of that divided by the norm of h. If the limit of that is 0, this is called the Fauché quotient. If that is 0, then that means that the map is real differentiable at p. And the differential is L. So, all right, so that's just a quick reminder. This is what we mean by differentiability for a real valued mapping from Rn to Rm, all right? So this differential is playing the role that derivative does in calculus 1. If dpf exists for each p and u, we say f is differentiable on u. The differential itself is actually a mapping from u to linear transformations from Rn to Rm. So it's an operator valued map, actually. That's what the derivative is in general. I should say differential. I try to say differential. So, now, lest you think I'm crazy, all 3 of these students have seen this definition before, so it's not insane. It's just partly insane. But anyway, so if f is a function from, a subset of, that's supposed to be Rn right there. I'm missing an n. Oops. Then you can write component functions for f, all right? Each component function is real valued, whereas f is generally vector valued. The differential itself is a mapping from a subset of Rn to a subset of linear transformations! Exclamation point. Very exciting. All right. So a next theorem, which I won't prove, but it's easy enough to prove, is if you have a function, again, there's supposed to be an n here, and these are the component functions, well, then f is differentiable at p if and only if all of the component functions are differentiable. All right, so, and that differentiability would be judged by the Frechet quotient for each component function, okay? So, on the other hand, we can define the ith partial derivative. So the ith partial derivative is simply defined in terms of a difference quotient, like this, right? So you guys know, you just take the derivative, varying just the ith coordinate and fixing the rest of them. This is a formula for the ith partial derivative, right? And if you can do that at each point in the set, that defines the ith partial derivative function. So basically, you're studying the change of the function along this linear path, right? T maps to f of p plus t e to the t. Well, this is not a linear path, right? This is but the image of a linear path in the domain. It's the curve in the RM. All right. So theorem: if you have a function, then the partial derivative of the whole map exists if and only if the partial derivatives of each component function exist. So we've got, again, this interplay between the whole function and its component functions at the level of partial derivatives. And more, not just that, the partial derivative of the whole function is the vector of partial derivatives of the components. All right? And a place you've already done this is Calc 3. So if we have a parameterization of a surface R as x, y, z, usually we use u and v for the domain. Then like partial u is this, partial v is that. We call these the partial velocities, right? You take the cross product of these, it gives you the normal vector to a surface, right? That's an example of this kind of calculus. So the next big theorem here is that if f, and again, man, look at that. Still, see, there's an n there. I hate that I printed these. If this is differentiable at p, then the directional derivative exists. And here's the relation between the differential and the directional derivative. The differential, when you feed it ei, is equal to the ith partial derivative at the same point. Now, this differential is a linear map. You guys tell me from linear algebra, you take a linear map and you feed it ei, what's that give you? You have a linear map of column vectors of R. This is a linear map from Rn to Rm. I take a linear map of ei. What is that for the linear map? In terms of the standard matrix.
Oh, that's one of the columns over there.
Yeah, it's the ith column of the standard matrix. So what this means is that the ith column of the standard matrix of the differential is the ith partial derivative. And as such, we can write the standard matrix of the differential like so, and it's actually all of these partial derivatives. This is called the Jacobian matrix of the map. So the Jacobian the Jacobian matrix, I'm not about to say that's all, folks, but I'm not giving up yet. I'm going to get to a good stopping point. We're not quite there yet. So whatever minutes that you think you went over, I'll show you how it's done. It's here. So we have I've got the n now. Check that out. That's nice. So u is subset of Rn, mapping the Jacobian matrix of f as this, and you can either write it as concatenation of partial derivatives of the map, or as this box of partial derivatives of the component functions, or if you like, it's a stack of gradients. Right? The gradient of the first component function, gradient of the second component function, gradient of the mth component function. This is the Jacobian matrix. Now, so for a function that's real valued, the Jacobian matrix is just a gradient vector. All right? It's just a 1 by n matrix like this, and we talk about that in calculus 3, right? We do talk about the Jacobian matrix a little bit for change of variables theorem. But it's just because it's a necessary thing for us to change variables. Our heart's not really in it in Calculus 3, typically, because it's not really supported by the textbooks that we use, unfortunately, because they're dumb. But sorry, but they are. Anyway, so here is a generalization of the mean value theorem for real valued functions of n variables. This much is true. If you have a function from Rn to R, differentiable, and we'll use the notation this notation I'll continue using throughout these notes. If I have an interval, like a parent interval from A to B, and A and B are points, this is the line segment from A to B, just like we did in complex, but now in Rn. And so there's the parameterization of a line segment from 0 to 1. If that's the case, then there exists C in the line segment such that the gradient at C, dotted with the difference, the displacement between the endpoints A and B, it's equal to the difference of the function between A and B. And this is easy to prove. It basically just rests on the chain rule from Calculus 3, namely that if you differentiate a composite function, it's the gradient of the function evaluated at the path times the derivative of the path. But the derivative of the path is exactly B minus A here, because gamma is the parameterization of the line segment. So, yeah. But on the other hand, H is a differentiable function on 0, 1, so you can apply the mean value theorem on it. And so like H of 0 minus H of 1 has to be equal to, divided by 1 minus 0, has to be equal to H prime of C for some C between 0 and 1. And when you sort through everything that's in front of us here, I used frac C just so it looks different. Frac C is my number between 0 and 1, which is given to us by the ordinary mean value theorem. And but H of 0 is f of A, and H of 1 is f of B, and as such, we get the theorem. Yay! So there is this generalization of the mean value theorem, and you might hope that this generalizes for, so this only works because the range of the function is real valued. If the range of the function is not real valued, everything falls apart. Everything falls apart. So let me show you how. So for instance, in the complex case, if you have, f equals to u plus iv, the component functions are u and v, right? The line segment from A to V, we can apply, we can apply the previous theorem to the real part and the imaginary part separately, and we can get gradient of u c1 and gradient of v c2 such that these conditions are met, right? And then the Jacobian is actually, it's a stack of the gradients of the real and the imaginary component functions. And so we can write, Jacobian of f of c times b minus a is equal to that. But the catch here is that we need the same c both places, because you can't evaluate a Jacobian matrix with c1 on the top row and c2 on the second row, and that's the problem. There's no reason for this C1 and this C2 to be equal. And as such, this calculation doesn't happen. And yet I did it in complex last week. Right? You remember? I said mean value theorem, remember that business? And the reason that worked is in the remark right here. If we happen to know that the C1 and C2 are in AB, and that AB happens to be an interval which is shrinking to a point, then we can make the C1 and C2 get really close together, and then in the limit, we're allowed to use the mean value theorem, but only in that tight limiting sense. That's the way that we used the mean value theorem to prove the ML theorem. It was that calculation. But anyway, short of that, we can't do it. Yeah.
I just remember you asked us to prove that on homework last year.
Yeah, it's not true. Yeah, it's not possible. But what ends up being true, yeah, if you Google mean value theorem for complex analysis, you will find ugly things. You will find ugly things. Anyway, I'll just say that. So a corollary to what we just proved, though, would be this, is that if you take the absolute value, you could say that's less than or equal to the max of the gradient, and it turns out that this corollary, which is a simple consequence of the Cauchy-Schwarz inequality to what we just proved, this is what generalizes to mappings. It turns out we can generalize the mean value theorem to this, all right? Now, that is probably the right place for us to stop today. So next time we'll pick up here, and I will use the projector at the start because, trust me, it's bad past here. And so what we're going to do is we're going to prove the mean value theorem for mappings, and then we'll see that you can use that to prove the inverse inverse mapping theorem. All right, so yeah, I think that's a good place for us to stop. I'm getting tired, so I know you guys are probably tired of listening to me. Thanks, guys.